Welcome to the Explainer. Today, we are diving into something pretty important. When a system, an AI or some kind of test, makes a prediction, how do we actually know if we can trust it? We're going to break down the tools the pros use to measure performance, and we'll even uncover some pretty surprising statistical traps along the way.
So let's just jump right in with a scenario. Imagine a doctor tells you that a new medical test is 99% accurate. Great, right? But then your result comes back positive. Now, your first instinct is probably to panic. I mean, who wouldn't? But what if I told you that panicking might be, well, a huge overreaction? We're going to come back to this, so just keep that question tucked away in your mind.
To figure out that puzzle, we've got to get our heads around a really basic idea. When we're talking about predictions, not all mistakes are the same. Not by a long shot. Just counting up what's right and what's wrong really isn't going to cut it. And this slide really drives that point home. Just think about it for a second. Let's say you're working in a toy factory and you accidentally toss a perfectly good action figure into the recycling. What's the real cost there? A couple of cents? But what if a medical AI makes a mistake and tells a sick person they're totally fine? The cost there could literally be someone's life. The consequences are in completely different universes.
So here's the absolute key takeaway. We have to care about the type of error that's being made. A simple number like an accuracy score totally hides this critical detail. And to really see what's going on under the hood, we need a much better tool.
And that tool is called the confusion matrix. Now, I know the name sounds like it's designed to make things more confusing, but I promise its job is to bring total clarity. It's basically a simple grid that helps us sort every single prediction into one of 4 buckets, giving us a perfect snapshot of how a system is performing.
Okay, so here's what one looks like. On one side, you have the actual value. That's the ground truth, what's really going on. And on the other side, you have the predicted value. That's what our system said was going on. And by comparing those two, we can sort every single outcome.
First up, we have the true positive. This is a win. Reality is yes, and the system predicted yes. A person is sick, the test catches it. Perfect. Simple enough, right? And just as good is the true negative. This time, reality is no, and the system also predicted no. A healthy person is told they're healthy. So these 2 boxes, true positive and true negative, these are all of our correct answers. All right, now let's get into the errors. A false positive. This is when the system cries wolf. The truth is no, but the system yelled yes. It's a false alarm. So a healthy person gets the scary news that they might be sick. This causes a ton of unnecessary stress, for sure. But hey, at least the real problem wasn't missed. And last, but definitely not least, is the false negative. Honestly, this is often the most dangerous kind of error. The reality is yes, but the system completely missed it and said no. A sick person is told they're healthy and just sent on their way. This is that high-cost error we were just talking about. Okay, so now that we know how to sort all our results, let's see how this builds into the 3 most important metrics for judging any predictive system: accuracy, precision, and recall. And trust me, each one tells a very different and very important part of the story. So first, there's accuracy. This is the one we all kind of know. You just take all the correct predictions, your true positives and your true negatives, and divide by the total number of guesses made. It gives you that quick, high-level summary. Overall, how often was the system right? But, and this is a big but, as we're about to see, it can be super misleading.
Next up is precision. This asks a much more specific question. It asks, of all the times the system raised its hand and said positive, how many of those times was it actually right? You can kind of think of this as a measure of its confidence. When it says yes, how much can you actually believe it?
And then you've got recall. Now this asks a completely different question. It says, of all the things that were actually positive in the real world, how many did our system manage to catch? This is all about completeness or sensitivity. Did we miss anything important?
Okay, we're armed with our new tools. It's time to go back to that first question about the medical test. We are about to spring the 99% accuracy trap, and you're going to see exactly why our gut instinct can lead us so wrong.
So let's lay out the full picture. We've got a town of 10,000 people. There's a rare disease, we'll just call it morbus pollicus, and it only affects 1% of the population. So that means 100 people are actually sick, and the other 9,900 are healthy. And our test, well, it has what sounds like amazing stats. It correctly spots sick people 99% of the time, and it correctly clears healthy people 98% of the time. Sounds pretty good, right?
Right, so let's actually map this whole thing out. We start with our 10,000 people. We know that 1%, so 100 people, really do have the disease. And that means the other 9,900 don't. Now let's just apply the test success rates to each of those groups.
And here it is, our final confusion matrix. Now just look at these numbers. Out of the 100 people who are actually sick, the test does a great job. It finds 99 of them. Those are our true positives. It only misses one person, our one little false negative. Awesome! But now look at the 9,900 healthy people. The test incorrectly flags 198 of them as being sick. Those are our false positive.
Which brings us to the final critical question. You get a positive test result. What is the actual, real probability that you are sick? Well, to figure this out, all we need is our precision formula. We just take the number of true positives and we divide it by the total number of positive predictions, which is our true positives plus all those false positives.
And the answer is just 33%. Seriously, let that sink in for a minute. A test that sounds 99% effective gives you a positive result, and yet you still have a 2 in 3 chance of being perfectly healthy. And the reason is that the disease is so incredibly rare that the small 2% error rate on that huge number of healthy people creates a mountain of false alarms that just completely dwarfs the number of real sick people it found.
So the most important lesson here is that a big, flashy number like 99% accuracy can be totally meaningless without context. In our story, the most important piece of context was the base rate, just how rare the disease was to begin with. This is why understanding the difference between accuracy, precision, and recall isn't just for data scientists. It's essential for making smart decisions in a world that's just full of data. The question is never just, is it right, but how is it right, and maybe even more importantly, how is it wrong?